Hello everyone, we are the KVH team. This is the upgrade of mechanical response testing equipment. My name is Brittany Perkins, this is Dan Wiskruski, and our team lead for this project, Nick Castro. Our client is KVH Industries. They were founded in 1982 and are located in Middletown, Rhode Island. They are one of the world's leaders in designing, assembling, and testing high-performance sensors and inertial navigation systems. They also work with residential, commercial, and military applications. So this is our original design of the tensile tester. Our original design was hand cranked, had an aluminum frame, and also had the ability to measure load. KVH Industries needed a device that could test multiple materials and have a deflection of a thousandth of an inch. So this is our team contributions. For this project, we really didn't have individual roles. Rather, we all kind of participated in communication, designing, SolidWorks, and machining. To start out this project, we had to do a lot of hand calculations. We did a lot of hand calculations, so we don't have them all on the board because there's just too many. But some of them were our frame bars, the lead screw, base thickness, sensors, spring, and bolt analysis. For the frame bars and the bolt analysis, we kind of just really needed to know how much the frame and the bolts could handle. So what we did for that was we went off a factor of safety and then looked at how much the material could hold. And based off of our factor of safety, the material could hold way more than what our factor of safety was, so it passed. For the base thickness, this was a problem that we were dealing with a lot. We needed a less than 1,000th of an inch for a deflection. So we did calculations on this to see what kind of thickness we would need on the base. We tested aluminum and steel for this, and for aluminum we would need 5.6 inch base, and for the steel we would need 3.9 inches. Now I'm going to hand it off to Dan, who's going to talk about the simulations.
So after we had validated that the machine was indeed safe, and we just needed to get the deflection down so we could get a measurement within the tolerance that the company wanted, we developed this simulation model, which has slightly simplified geometry on the 80-20 beams and is a half model, just because of the fact that a symmetric distribution gives a symmetric result. So we could just simulate half of it at a lower computational cost. As you can see, the main force distribution is right there, where the sample would be connected to the base and then top the bed, then pulled apart or pushed together. During these simulations, we did find one screw that, due to stress concentrations, would shear off, and that was originally around here on the base plate. But due to the fact that we wanted less deflection, we got rid of the two plates that was holding together just because they were pulling apart and deflecting a lot more. So we just didn't have that bolt in the final design. Moving on through our design process, we eventually settled on this design here, and as you can see from the table, we have in the blue the 1,000th deflection that is acceptable, and in the red and gray we have the deflection of the sensor during a tension test. And as you can see, it does get quite close to 1,000th, but it does stay under. So deflection measurements of under 1,000, around 1,000, should be possible for the displacement sensors. Going quickly through our design process, we originally were trying to get the displacement down by thickening up the base and just getting enough heft and moment of inertia to resist the bending. But as you can see from that, it required a lot of material and it was a very inelegant solution. So we opted to, instead of trying to get the base to deflect below 1,000th, we would use two sensors, one to characterize the deflection of the machine, the other one to measure the sample, so we could subtract one of them out in the final measurement. to try to isolate the sensors, we started with a completely separate sensor mount, but the company wanted an all-in-one device that was, so they didn't have to keep track of multiple parts. So we combined it with the wheelbase on the casters and had that supports there to keep the bar upright. Just looking at our final design now, we have the accuracy chevron here, which is just holding up the sensor bar, what we're mounting our sensors on. And it is less noticeable, but we have an extra leg that can be extended down to the floor to give it more support during tests, as well as the main feature, the motor, which was replacing the hand crank, and the drive system with a ball low tensioner on it. One of the less noticeable things in that picture is the legs have these V-notch cuts on them, simply because the central machine is still deflecting more than 1,000th, and we need to isolate the sensor mount from that deflection. Having our final design, we moved on to machining. A couple of the interesting challenges we had machining was the nice accuracy chevron was at a very odd angle, and we had to connect that with L brackets. So getting those to the proper angle on a vise was a bit difficult, as well as the machining of the 80-20 bars, cutting them off, and drilling and end milling the counter bores on the holes there, since they have a lot of little contours, as well as we had experience end milling the accuracy blocks and whatnot for the various parts. Having the machining finished, the final machine comes together to look like this. As you can see, we have the motor with a motor made to the existing pulling system. We have the same force output, and that's the final machine. Moving on to Nick with our testing plan.
Thanks, Dan. So for our testing, first we need to validate our simulations. To do this, we'll attach the bed to the base and then start applying forces. Once we start doing that, we'll then measure the deflection at various points of interest. And once we accumulate that data, we'll then be able to match it up with our simulations and prove whether or not our simulation data is accurate. Excuse me. So, given that our simulation data is accurate, then we move on to our accuracy testing of our device. For that, we're then going to compare it to a UMass machine, and we're going to run 5 tests of 3 different materials each on each machine. In doing so, we'll collect our data and then compare that data and then run statistics analysis to see how accurate we are. The 3 materials we've chosen would be HDPE, LDPE, and nylon. So as anything in life, we ran into some challenges. First off was ordering parts. We soon realized that not all suppliers are as readily available as MasterCard. So we had some a little bit of time delays waiting for some electrical supplies and other stuff like that. So that definitely put us a little bit off schedule. Our second one was finding a cost-effective sensor that both met our resolution needs as well as our data output needs, as sensors can go for thousands of dollars depending on how accurate and all the different features that you're looking for. Our third challenge would be machining. It took a little bit longer than we had anticipated. This is a given though, as for the accuracy and precision that was required, that takes patience and craftsmanship. And our last main challenge is, as a team of mechanical engineers, we were able to get electrical help from a junior in ECE for the spring semester. We feel as though, given a full time span with him, we definitely would have been able to accomplish all the goals that we had had. Some of our clients' comments, because the machine doesn't work right now, they can't say too much, But overall, based on the mechanical aspect of it, they're happy with our work, and they can definitely tell that we've done our research and we've learned a lot and seen it through to the end. So for our budget, we were initially given $1,000. Of that, we spent $850 making it so our device can be capable of the applied forces that we're looking to put on it. So I know 850 out of the 1,000 seems like a lot, but compared to 2,250 pound Instron 4202, which is supplied by a Frank and Bacon machinery supply, that goes for $26,500. And if you do that cost ratio, we're definitely winning on that side. And 2,500 pounds versus 2,250, we're still on the plus side. So overall, we're doing all right. For our schedule, it starts with meeting your advisor, then we meet our client, we get to know what they want and what they need from a project. And from that point, we can do our research and start design iterations until we come to a point to where both our client and ourselves are happy with the design. And when we get the okay, we start ordering parts, we start machining, and we get to the point now where we get to present our final design and our ideas to you. In conclusion, we start before with our hand crank machine. It had the widespread legs, didn't have any means for any displacement testing. And now to finish the semester, we, as you can see in the top right in figure 25, you can see the motor we've added. We have the new steel base, we have more supports, we have the notches in the legs, and we still have the force displacement, as well as we have we added the testing data on top of, or underneath the load cell. That way there's always a consistent point of measurement. Acknowledgements, thank you to everyone involved that really helped us get to where we are, especially Paul, who's very patient with us, great guy. Marcelo, the junior in ECE, he was very helpful for us in doing research, calculations, and electrical programming. Don Foster was a huge mentor for our project, as well as Professor Chalavandra, who was our advisor, and Professor Perdue, who was a class instructor. And also shout out to Tracy McDonough, who helped us with some SolidWorks.